Hello, this is Physics 2212 Lab 6. The purpose of this lab is to observe the effects on a magnet as it falls through an aluminum tube, and we want to observe the magnetic field created by the magnet as it falls. The models include a real-life model that had an aluminum tube and a magnet, and a computational model on GlowScript. Zooming in to our fundamental physics principles, we have first Newton's second law, and we really just want to use this for the force of gravity, which is 9.8 meters per second squared. And then we have the Biot-Savart law, where Km here would be mu naught over 4 pi. And then you can see it on screen, and we need this to calculate the change in the magnetic flux. And then we're going to have Faraday's law, but we really want to focus on this far right part right here in order to get the magnitude of the change in flux over the time. And then for a brief preview of the results, we got an average time of 1.54 seconds in the real-life model. And then for the computational model, we got an average time of 2.117 seconds. And we'll explain how this could have happened later. For systems and surroundings, the system is the magnet, and the surroundings include the aluminum tube, the earth, and everything else in the environment. And the initial conditions really just include like the constants, and then we start from time is 0 and velocity is 0, and then the measurements of the mu mag and the mass of the magnet. And then for the experiment, we began by taking a bar magnet and letting it fall down an aluminum tube, and we repeated this process 5 times and recorded the data for each type. And then we took the average times, and then we made our GlowScript model based on the measurements of the items we used. And here are pictures of like the experiment. And then to start off our code, we begin by defining the constants that we need, like the resistivity of the aluminum, gravity, the mu naught over 4 pi constant, and then we have the measurements for the mass and the mu mag of the magnet from earlier, along with the velocity and the time. And then here we're just taking like measurements of the tube and the foil, and then we're just finding the radius. And then after that, we like have this function over here that helps us calculate the magnetic field of the magnet, and it's just using one of the formulas that we showed earlier. And then like we're also like calculating the flux of the magnet in this bottom function. And then from there, like all of this code is just in the loop, and we're just like finding the total force on the magnet. So we're gonna find the gravity on it, and then we're also gonna find like the B field at each of the rings, and then we're just gonna add them up for the force on the magnet. And then right here is just updating the velocity and the position of the magnet. And here are the results of the code. As you can see, this like snippet of the graph right before it just goes constant is really just the magnet falling down, and then we can see that the magnet's trying to like it like has a flux, so that way it can try and balance out the force of gravity as it falls down. And then like this snippet at the end is just it going out of the tube and falling down. The similarities are that the numbers are within the same scale, but we can see a slight difference in like the numbers we get, since we got like 1.54 for the real-life model and 2.117 for the computational model. The error might have just been human error, since we might have calculated some things wrong when we took the measurements, and we also like calculated mu again for this lab. What if the resistivity was as close to 0 as possible? Then basically the magnet would fall slower, since with Ohm's law, with V equals current times resistance, we would need a much stronger like current as it falls. So it'll fall slower. And then like if we had holes or slots in the tube, then basically we'd have the magnet would have to like counteract less rings of current, so that way it can just fall faster. Thank you for watching, and goodbye.